Okay, do you have any questions? Okay, then, so let's, if you remember, not last week, but the week before, we had started the rotation, discussion of the rotation. Now, let's just make a short review of what we had done in rotations. Let's say we had considered, as an example, a rotation around the z-axis. So basically, if we rotate the coordinate axis by an angle theta, then considering any vector v, we had x component, y component, and the z component in the original coordinate axis, or in the rotated coordinate axis, we had the x prime hat component, y prime hat component, and z prime hat component. And we had certain relations between the two. If you look at Vx prime, the new x component was, it's just the v dot x hat prime, which is Vx x hat scalar product x hat prime plus Vy y hat scalar product x hat prime plus Vz z hat scalar product y hat prime. And if you consider, since we are considering a rotation around the z-axis, y hat prime and z hat, they are orthogonal to each other, so this is 0. X scalar product with x hat prime just gives me the cosine of the rotation angle, and y scalar product with x hat prime just gives me the sine of the rotation angle. So this is the new coordinates in terms of the old coordinates. And similarly, if you do the same thing for Vy prime, you would get that Vy prime is minus Vx sine theta plus Vy cosine theta. And Vz prime is equal to Vz. So we could write this as a matrix. This is equal, the new components is equal to, in terms of the old components, we can just obtain it by a matrix multiplication. Cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. Vx, Vy, and Vz. And then what we did was, let's just consider a very small rotation, theta, much smaller than 1. So we can just expand this. Cosine theta is approximately 1 minus theta squared over 2. Sine theta is approximately theta. So Vx prime, Vy prime, Vz prime, this is equal to 1, 1, 1, theta minus theta, 0, 0, 0, 0, plus terms of the order of theta squared, multiplying the old coordinates. And so we also wrote this as 1 minus I theta, let's say mz, multiplying Vx, Vy, and Vz, where we define this mz to be I minus I 0, 0, 0, 0, 0, 0, all zeros. Now, the reason why we have introduced that minus I is so that mz is Hermitian. And we can do the same trick that we do quite often. Let's denote this by some rotation matrix R for rotations around the z-axis by an angle theta. Rz of theta for any theta, this should be equal to limit as n goes to infinity, 1 minus I theta over n times mz raised to the power n. So what we are actually doing here is, well, this expression for Rz of theta is valid for theta very, very small. So, but any rotation we can write as a collection of very small successive rotations around the same axis. So this is basically what I'm doing. A rotation by theta is n rotations acting successively by angle theta over n. Whatever the value of n is, that is always satisfied. Now if I take the, well, let me add one more step over there. Rz of theta is Rz of theta over n raised to the power n for all values of n. And if n is sufficiently large enough, eventually we take the limit as it goes to infinity. Theta over n is very small. Since theta over n is very small, we can use this expansion over there of Rz as 1 minus I theta mz. If you take the nth, if you take this limit is nothing but the exponential of minus I theta mz. Now, there is nothing quantum mechanical here. We are just dealing with ordinary three-dimensional vectors. And this is the rotation matrix for rotations around the z-axis. Now let's work, and any questions up to here? Now we can just repeat the same thing for the x and the y components. If you take the if you rotate around the x-axis, let's say x is out of the screen, y is this one, z is this one. If you rotate around the x-axis by the angle theta, just like the previous case, well, the x-coordinate doesn't change. The new y-coordinate will be just v dot y hat. This will be v y, now y prime hat, y hat dot y prime hat plus v z hat, scalar product z prime hat. V y prime is just the y, and this is our y prime, this is our z prime. Y dot y prime is cosine theta, and z dot z prime, no, sorry, this is still y prime. Z dot y prime is sine theta, and vz prime will be minus vy sine theta plus vz cosine theta. So our rotation matrix for a rotation around the y-axis by an angle theta, x prime is not affected. No, this is rotations around the x-axis. X-coordinate is not affected. Y-coordinate just becomes, here we have cosine theta, sine theta, minus sine theta. If theta is much, much less than 1, this r x of theta, we can still write it as 1 minus I theta my, mx. And this time, this is equal to 1, 1, 1. If you just make the expansion of the theta squared terms, cosine just becomes a 1. Well, sine terms just become theta. 0, 1, minus 1, 0. So mx is just 0, 0, 0, 0, 0, I, 0 minus I, 0. This is our mx. Let's look at rotations around the y-axis. So this is our x, y, and z coordinates. So if we rotate around the y-axis by theta, this is my new z prime, this is my new y prime. Now, do you follow why I draw the x-axis on this side? Not towards the right, but towards the left. You see, if you look at before, when I consider rotations around the x-axis, and I draw the z-axis pointing towards the top, y-axis is towards the right, not towards the left. But when I consider rotations around the y-axis, the x-axis is towards the left. So that is a right-handed coordinate system. And the rotation direction is always determined by, again, the right-hand rule. So if you're at some point in the y direction, so this is how I'm rotating my coordinate axis. Now this will make some sign change in the rotation matrix for y. So let's see, this is theta. Vx prime is Vx x hat dot x hat prime plus Vz z hat dot x hat prime. Now I'm not considering the y component because y scalar product with x hat prime is just 0. So Vx prime becomes Vx, no sorry, this is x prime. X hat dot x prime, this angle is also theta, so this is cosine theta plus Vz. The angle between z and x prime is now theta plus pi over 2. It's not pi over 2 minus theta, but it is pi over 2 plus theta. So here I have a minus sine theta. In Vx prime, Vy prime is just Vy, Vz prime is just plus Vx cosine theta plus Vz, no, this is sine theta plus Vz cosine theta. So my rotation matrix around the y-axis by an angle theta is now Vx prime is cosine theta minus sine theta 0, no, sorry, cosine theta 0 minus sine theta. Vy prime is just Vy, Vz prime is Vx is multiplied with sine theta, and Vz is cosine theta. This is my rotation matrix. Again, I can just consider a Taylor expansion around theta is equal to 0. This just becomes the unit matrix plus theta times 0, 0, minus 1, 0, 0, 0, 1, 0, 0. And if I write this as 1 minus I theta my, my is just 0, 0 minus I, 0, 0, 0, I, 0, 0. So this is my generator of rotations around the y-axis. Now let me just collect them all. This is x. And mz. Zero I minus I, 0, 0, 0, 0. Yeah, this is my mz. X and z, they look very similar. I mean, if you look at mx has zeros in the first column, first row. That's the first coordinate. And what remains is this matrix 0i minus I, 0. If you look at mz, it's exactly the same form. It has the same form. Z is the third component, so the third row and third column is all zeros. What remains is exactly the same matrix. And y has, well, somewhat similar. Y is the second coordinate, so second row and second column is they're all zeros. The y coordinate doesn't change on the rotations around the y-axis. What remains is not this 2 by 2 matrix. If you remove the second row and second column, what remains is not this 2 by 2 matrix, but minus this 2 by 2 matrix. Now let's look at their commutators. These are just matrices, and even in classical physics also rotations do not commute. So if you just consider, for example, two rotations, first rotation is around this axis, then a rotation, let's say, around this axis. This is different than first rotation around this axis, then rotation around this axis. They are different. And let's consider the commutators. Let me just calculate one of them, mx, my commutator, which is mx is 0, 0, 0, 0, 0, I, 0, minus I, 0. My is 0, 0, minus I, 0, 0, 0, I, 0, 0. Minus my mx. This is equal to, if you just multiply, the first row is all zeros, the second row is minus 1, 0, 0, the third row is again all zeros. If you change the order of product, what you would get is just the Hermitian conjugate of this one, or the transpose of this one. They are the same thing. Or did I take the correct things? Yes. And this is equal to 1 minus 1, 0, all zeros here. Or this is equal to minus I times 0I, 0, minus I, 0, 0, 0, 0, 0. And this matrix element is just Z. Using this information, you can also calculate the commutator of, these are the commutators of rotation, of generators of rotations. If you would calculate, let's say, the rotation around x by epsilon, then around y by epsilon, minus the same thing in reverse order. This is equal to 1 minus I epsilon mx plus terms of the order of epsilon squared, 1 minus I epsilon my plus terms of the order of epsilon squared, minus the other way around, if you open up the parentheses, you will get, well, we would probably need the higher order terms, but let's see, 1 minus I epsilon my minus epsilon squared mx my minus, minus I epsilon mx minus 1 minus I epsilon mx minus I epsilon my plus minus epsilon squared my mx. There will be terms of the order of epsilon cubed. Now, ones will cancel, my's will cancel, mx's will cancel, and we would end up having epsilon x, epsilon squared, my mx minus mx my plus terms of the order of epsilon cubed. But this we had calculated, this is just I mz. So this is equal to 1 plus I epsilon squared mz. No, there's no 1. Which is rotations around the z by minus epsilon squared minus 1. Plus terms of the order of epsilon cubed. Again, I repeat, these are just classical rotations, nothing quantum mechanical up to this point. Any questions?
Diran notasyonuyla şeye mi geçeceğiz? Yani o doğru mu her zaman? Klasik bir komütasyon alıyoruz, bir operatör alıyoruz, bunu gidiyoruz, h-barla çarpıyoruz, kuantum mekanik sayı yorumuna gidiyoruz. Bu doğru mu gerçekten?
Let's see. So, let's look at translations. I mean, we had already looked at translation before. Let's consider translations from a different perspective, from the wave functions. I will consider translations of the coordinate axis. So, this is, let's say, my first coordinate, and then I have my second coordinate. They just differ by translation along the x, let's say. This is my xy axis, this is my x prime, y prime axis. And if you consider any point, it will have, that point will have the coordinates xy and z, or it will have the coordinates x prime, y prime, and z prime. And these coordinates are related to each other. Z prime is equal to z, y prime is equal to y, and x prime is equal to x minus a. This is my a. I just translate by a. Now let's suppose I have a coordinate, I have a wave function, psi, x, y, and z, written in the original reference coordinate axis. And I have a similar wave function, let's say psi prime, it might have a different slightly different functional form, x prime, y prime, and z prime. And again, for simplicity, let's assume that my wave function is just an ordinary function. It's not a vector function. It only contains the information about position and no direction. Now, what do I expect if these two wave functions they correspond to the same state? Their value at this point, no matter which coordinate axis I use to describe that point, should be the same. So these two things has to be equal to each other. Do you agree? You see, coordinate is something that we invent just for our mathematical simplicity, let's say, to be able to deal with the points in a mathematically simpler way. So whatever the coordinate axis I choose, the value of my wave function at this point should be the same. It shouldn't differ if I change my coordinate axis. Because no matter which change I make in my coordinate axis, that point is exactly always the same. It's just I will use different numbers to denote the same point. So in the x, y, z coordinate system, I will use some set of numbers. In the x prime, y prime, z prime coordinate axis, I will use a different set of numbers to describe exactly the same point. So my wave function at that point should have a unique value. So this is basically why these two wave functions in different coordinate axes should be related with each other. So psi prime, x prime, y prime, z prime will be equal to psi of x. Well, x is x prime plus a. Y prime and z prime. The others are the same. Well, let me do a rotation. Let me do a Taylor expansion now. This will be equal to psi of x prime, y prime, z prime, plus a times del over del x prime, acting on psi, plus a squared over 2 factorial del over del x prime squared, acting on psi, etc. Psi prime of x prime, y prime, z prime, this is equal to 1 plus a del over del x prime plus a del over del x prime squared multiplied with 1 over 2 factorial plus etc. They are all acting on psi. This is equal to the exponential of a del over del x prime operator acting on psi. This is equal to exponential of minus I over h bar a times I h bar del over del x prime acting on psi px prime psi. So this is just another way of driving that translation operator. Then of course we identify it with the momentum operator and we show it by a derivative. Now let's come to the rotations. Well, let's redo this thing by our ket notation. What do we mean? What do we calculate by our kets? Now psi of x, y, z is just psi r. Psi prime of x, y, z. Well, there are a couple of ways that we can write it. Well, it's the same ket. So it's actually psi. But the xyz ket is now the eigenket in a different coordinate axis. Or this is equal to psi. Now this x prime, y prime, z prime ket is actually x minus a, y, and z ket. Now let me put a prime over there. Or you can say that, okay, I will use the same notation, x prime, y prime, z prime, and psi prime, whichever one you like. Now we will do a similar thing for rotations. You see, if when I make a rotation of my coordinate axis, let's say, my ket will look different. So if I start with a ket psi, I will say that after rotation, it will become some other thing, psi prime, which I can write as some matrix, some operator acting on psi. Of course, this rotation, let's say I have a rotation matrix R. Now, for each rotation, there will be a corresponding operator. Now, there are a couple of things that I would rather have this operator, some properties of this operator. Let's see, I can consider two rotations, two successive rotations. First, I rotate by R2, then I rotate by R1. But I know that just in a real space, just any successive two rotations, I can write it as a single rotation. So this is some other rotation, R3. Now, what these rotations do on my kets will be, well, R2, a rotation by R2 will just modify my kets based on the R2. A rotation by R1 will change my kets by R1. But these two successive rotations should be the same thing as a single rotation, R3. So the product of these two operators should do exactly the same what this operator corresponding to R3 does. So this is one property I require my rotation operators acting on my Hilbert space. One of their properties, should be one of their properties. Now what else I know? Well, if I consider, let's say, a rotation around an axis n by an angle theta, if I rotate around the same axis by an angle minus theta, I should get no rotation. I just rotate in one direction and then back. It's the same thing as no rotation. Well, this tells me that dr1 multiplied with dr2, now dr and theta, well, no rotation is just the identity. So this is another property that they should have. Well, if I have three rotations, R1, R2, minus R1, R2, R3, well, first I act with R3, then I act with R2, then I act with R1. Well, R3 and R2 I can consider as a single rotation, and then I act with R1, I get a single rotation. Or I first act with R3, and then the action of R1 and R2, I can consider it as a single rotation. These two should be the same. They should be associative. So the corresponding operators should satisfy the same property. Now let's look at this one. You were asking about the commutators. Well, you see, if you consider, let's say, around x-axis by epsilon, this is equal to some rotation minus I epsilon mx. Well, this is a rotation that is very close to the identity rotation. Identity rotation corresponds to the to the identity operator in my Hilbert space. Well, this rotation deviates slightly from the normal rotation, so the corresponding operator should also deviate by a very small amount from the identity operator. So I can write this as 1 minus I epsilon. Let me call that operator Jx. And similarly Jy and Jz. Now what do I know? I know that Rx of epsilon, Ry of epsilon minus Now there was a mistake I made. Let me just correct it. You see, if I make rotations in one direction and then back in one order or the same order is not the difference of rotation matrices, it's just the products of rotation matrices. So let's say if I first rotate around the x-axis by epsilon, then around the y-axis by epsilon, then I rotate around the x-axis by minus epsilon, then around the y-axis by minus epsilon. Let's see what this is. So basically I'm comparing our y epsilon, our x epsilon in one order and our y epsilon, no, our x epsilon, our y epsilon in the reverse order. And I'm just multiplying the inverse of this one with this one. So if the rotations would commute, then this I should obtain 1. Let's see what I have. Now, this is our y of minus epsilon is 1 plus I epsilon my plus terms of the order of I'm just ignoring all the terms of the order of epsilon squared. Times 1 plus I epsilon mx, 1 minus I epsilon my, 1 minus I epsilon mx. Let me multiply them. Well, 2 by 2, 1 plus I epsilon mx plus my, 1 minus I epsilon mx plus my. Well, I will need the epsilon squared terms also. This is minus epsilon squared my squared minus epsilon squared my squared plus minus epsilon squared mx squared over 2 minus epsilon squared mx squared over 2. I will ignore everything of the order of epsilon cube.